Let's talk about special quadrilaterals. We've spent the last few videos discussing parallelograms, rhombuses, rectangles, squares, trapezoids, and isosceles trapezoids, and in this video our focus is going to be on differentiating between each of those types of quadrilaterals. So first let's just categorize them in a good old-fashioned Venn diagram. Of course this one's a little bit more complicated than your standard Venn diagram because we have more than just three things we're comparing. The entire circle represents all quadrilaterals, so as long as it has four sides, it goes in the bubble. But within this bubble, we have some specific groups. This larger bubble is for parallelograms. A parallelogram is a specific kind of quadrilateral. It has two pairs of opposite sides that are parallel. And then we also learned some specific types of parallelograms that have extra information about them. For example, a rhombus. A rhombus is a parallelogram because its opposite sides are parallel, but it's special. It's more specific than a parallelogram because it has four congruent sides. We also learned about rectangles, which are parallelograms because their opposite sides are parallel as well, but they're more specific than just a normal everyday parallelogram because their angles, all four of them, are congruent. And then if you combine a rhombus and a rectangle, you get a square. A square is a parallelogram, that's why it's in this big parallelogram bubble. It's also a rhombus, which is why it's in the rhombus bubble, and it's also a rectangle, which is why it's in the rectangle bubble. So it has all of the properties of these three other shapes. It's a quadrilateral because it has four sides, it has opposite sides that are parallel, it has four sides that are congruent, and it has four angles that are congruent. But then we have this other bubble, which is for trapezoids. Trapezoids are not parallelograms, so they get their own bubble. Parallelograms have two pairs of opposite sides that are parallel, whereas trapezoids only have one pair of parallel sides. Within this bubble, though, we do have a specific type of trapezoid, and that's isosceles trapezoids. They have, again, the one pair of parallel sides, but if it's isosceles, that means that the other pair of sides are congruent. So this is one way for you to visualize how all of these shapes are related to each other. But let's also take a moment to look at all of their characteristics, because there's more than just parallel sides and congruent angles and such. We have to know things about their diagonals and their midsegments and a whole bunch more. So I challenge you to pause the video right now and see if you can figure out which of these boxes you should put a check mark in based on whether each of these figures has this characteristic. Pause the video and try it now. All right, let's see how you did. Which types of quadrilaterals have all four angles are congruent to each other? Well, that would have to be a rectangle and a square. What about having opposite angles that are congruent to each other? Well, that is one of the theorems that we learned about parallelograms. Their opposite angles are always congruent. And if it's true for parallelograms, then it's true for all of the different types of parallelograms, so you could say it's also true for a rhombus, a rectangle, and a square. Remember that rectangles and squares are even more specific than that. They don't just have two pairs, they have all four angles are congruent. Which shapes have two pairs of consecutive angles that are congruent? Well, that would just be isosceles trapezoid. If you have consecutive angles that are congruent, that means that they're on the same side of the shape instead of opposite sides of the shape. So that would not apply to parallelograms or any of the special types of parallelograms. But it also wouldn't apply to a normal everyday trapezoid. It only applies if it's an isosceles trapezoid. But what if we said that all pairs of consecutive angles are supplementary? That would be true for parallelograms, and therefore it's true for all of the special types of parallelograms. Whereas if you only have two pairs of consecutive angles that are supplementary, as opposed to all of them, that's for trapezoids. Those are basically the consecutive interior angles formed by the two parallel bases. Which of these figures have two pairs of opposite sides that are parallel? Well, parallelogram, obviously, that's the definition of parallelogram, and if it's true for parallelograms, then it's true for all of the special types of parallelograms. As opposed to having only one pair of opposite sides that are parallel, that's for trapezoids and isosceles trapezoids. If all four sides are congruent, that's true for a rhombus, which means it must also be true for a square because squares are rhombuses. Which ones have two pairs of opposite sides that are congruent? Well, that's one of the theorems we learned about parallelograms, so if it's true for parallelograms, then it's true for all of the special types of parallelograms. But if we only have one pair of opposite sides that are congruent, That's specific to isosceles trapezoids. Which figures have diagonals that bisect each other? Well, that's one of the theorems we learned about parallelograms, so if it's true for parallelograms, then it must be true for all of the special types of parallelograms. But it's not true for trapezoids. Which figures have diagonals that are congruent to each other? Well, we learned that's true for rectangles, and if it's true for rectangles, then it's also true for squares. But we actually also know that for isosceles trapezoids as well. Which ones have perpendicular diagonals? That was true for a rhombus, which means it must also be true for a square. Which ones have diagonals that bisect the pairs of opposite angles? That's true for a rhombus, which means it must be true for a square as well. And then the last two talk about midsegments, and we only talk about midsegments in reference to trapezoids. So a midsegment being parallel to a pair of opposite sides, that has to be the trapezoids, and the midsegment being equal to half the sum of the bases, or the average of the lengths of the bases, that again can only be true for trapezoids. So let's look at a diagram that has multiple types of quadrilaterals in it. We're told that ZVWU, so like this top part of this figure is a rhombus, and ZWXY, so this bottom part is a rectangle. And we're told each of these measurements. So let's just take it one variable at a time. If I want to solve for A, well, I see A in this variable expression and this one. So ZW is this line and YX is this one. Those are opposite sides of the rectangle, and we know that opposite sides of rectangles or opposite sides of parallelograms are equal to each other. So I can say that 21A plus 7 is equal to 24A minus 8, and then solve that equation, and we find out that A equals 5. So we can use that information to calculate the length of ZW. ZW would be 21 times 5 plus 7, so ZW must be 112 inches. And we can also calculate the length of YX doing the same thing, plugging in 5 for A. 24 times 5 minus 8 gives me the same answer of 112 inches. So this is what we know so far. Now let's see if we can solve for B. B appears here in the 8b plus 1 expression and here in the 12b minus 31 expression. So that's ZU and UX. ZU and UX. So those are two of the diagonal segments in this rectangle, and we know that since it's a rectangle, it's a parallelogram, and if it's a parallelogram, then the diagonals bisect each other. So that means that ZU must be equal to UX. So I can set 8b plus 1 equal to 12b minus 31 and solve. So B has to be 8, and that means I can plug it in to figure out the lengths of ZU and UX. So ZU is 65, and so is UX. And then the next variables that we're given are related to angles, so I'm going to pause on that for right now and continue with the rest of these side lengths. The next segment we're supposed to find the length of is YW. YW is this diagonal right here, and since it's a diagonal in a rectangle, I know that the diagonals are congruent to each other. That's a special property of rectangles. So since one of my diagonals in this rectangle is 65 and 65, I can conclude that the other diagonal is also 65 plus 65, which is 130. Then we're supposed to find the length of VW, and VW is one of the side lengths in this rhombus. And since it's a rhombus, all four sides have to be the same, so VW has to be 65, and the next thing we're supposed to figure out is ZV, which must also be 65 because it's the fourth side of that rhombus. So now we know all of the segment lengths except for ZY and WX. And we're going to have to go back a few units to figure out how to solve for ZY. Let's just focus on this part of the diagram right here, this triangle. And we would actually know that it's a right triangle since this is a rectangle and the angles in rectangles are all congruent, which means they all measure 90 degrees, which means they're all right angles. So this is a right triangle. So I just redrew the right triangle part of my diagram separately so I can focus on the important information. I know that ZW is 112 and YW is 130. So I can use the Pythagorean theorem to figure out the length of ZY. So solve that out and we find out that ZY must be 66 inches. Okay, cool. So we figured out all of the segment lengths in this diagram. Let's see if we can do something similar for all of the angle measures. To get started, we're going to need to use this variable information right here. We're going to solve for C. The two angles that we're told measurements for are ZVW, ZVW, so that's one of the angles in the rhombus, and ZUW, ZUW, so that's the opposite angle from the first one that we were given. And since a rhombus is a parallelogram, and parallelograms have opposite angles that are congruent to each other, I know I can just set those two variable expressions equal to each other and solve. So I find out that C is 21, and I can plug that back in to figure out the measures of angles ZVW and ZUW. They both measure 118 degrees. Next up, let's calculate the measure of VZU. VZU, we're really focusing on this angle right here. And if you just look at the rhombus, or parallelogram, because rhombuses are parallelograms, these two angles are consecutive angles, or these two angles are consecutive angles. Either way you look at it, the consecutive angles add up to 180 degrees. So I can say that angle VZU plus 118 is equal to 180. So the measure of angle VZU is 62 degrees. But next we're supposed to figure out the measure of WZU. WZU is part of that 62 degree angle. But since this is a rhombus, we know that the diagonals of a rhombus bisect the opposite angles. So since the entire angle measurement, VZU, is 62, each of the little angle measurements that are created by this angle bisector, they both have to be 31 degrees. So what about the measure of WZY? WZY. So that's one of the angles in the rectangle. And since it's a rectangle, each of its angles have to be 90 degrees. And that can help us to figure out the next answer, which is YZU. Since this entire angle measurement has to be 90, and we figured out that part of it is 31, the other part has to be 59 degrees. So we're doing pretty good on figuring out all these angle measurements. A lot of these we could actually copy and paste. We weren't asked for them, but these two angles would both have to be 31. This angle also has to be 118. This angle would have to be 31 degrees because of alternate interior angles, or you could say that this one is 31 degrees because of the base angles theorem. There's a lot of things that we could copy and paste in here based on numbers that we've already calculated. But there's one left to figure out that we don't know yet, that isn't an angle measurement that we've already calculated, and that's the measure of ZUY. Let's focus our attention on the rectangle. And we know that the rectangle's diagonals are congruent to each other and bisect each other. So I could put these markings on my diagram because the diagonals are the same, and if you cut the same thing in half, then all of the halves are the same. So how's that going to help me to figure out this angle right here? Well, let's just focus on this triangle. Isn't it isosceles? Since it has two congruent sides, it must have two congruent angles. And those are the base angles. The base angles are the ones that are both attached to the base, so both of the angles that are attached to side ZY must be the same measure. Both of these have to be 59 degrees. So you could say that this angle, the one that we're looking for, plus 59 is equal to 180, which means the missing angle measurement must be 62 degrees. Now you might be saying, wait a second, that's not how I solved for it. I just used linear pairs. And absolutely, that's totally another way to do it. On this kind of a diagram when there's so many angles to solve for, and at this point we know so much information about the diagram, there's almost always going to be more than one correct way to solve, so if you use linear pairs instead of isosceles triangles, that's totally fine, because you would get to the same answer of 62 degrees either way. So the last thing we'll look at in this video is just a few true-false exercises. If the diagonals of a quadrilateral are perpendicular, then it must be a rhombus. Well, that's not the only thing it could be though, right? Yes, it could be a rhombus, but it could also be a square. So a rhombus isn't the only shape that has perpendicular diagonals. Squares do too. What about if a quadrilateral is a rectangle, then it's also a parallelogram. Is that true or false? That's true. That's actually part of the definition of rectangle, is that it's a parallelogram with four congruent angles. So that's always true. If it's a rectangle, then it's always going to be a parallelogram. If a quadrilateral is a trapezoid, then it must have two congruent sides. Is that true or false? It's false. It doesn't have to have two congruent sides. It only has two congruent sides if it's isosceles. So it could just be a normal trapezoid that is non-isosceles and therefore would not have two congruent sides. And we'll actually be exploring questions like that much more in depth in our next lesson. We'll be taking all of the properties of special quadrilaterals that we've learned in these last few videos and applying them to determine what type of quadrilateral we're looking at based on the characteristics that have been given.